As the technology matured, ES split into three major technical variants, each operating on vastly different principles of physics and frequency spectrums. The first and most common variant is the radio frequency, or RF system. RF systems operate using the fundamental principles of wireless energy transfer at a high frequency of exactly 8.2 MHz. The transmitter pedestal at the store exit continuously sweeps frequencies around this 8.2 MHz mark, while a parallel receiver pedestal opposite to it captures the emitted electromagnetic flux. Inside every RF tag lies a passive resonance circuit, composed of an inductor denoted as L, made of a flat aluminum foil coil, and a capacitor denoted as C, integrated into the sticker's internal dielectric structure. The natural resonant frequency, denoted as F0, of this LC circuit is mathematically formulated by the classic engineering equation where F0 equals 1 divided by 2 pi times the square root of L times C. When an active tag enters the gate, it absorbs energy from the transmitter wave because of electromagnetic resonance. This causes a sudden, sharp voltage dip in the signal received by the opposite antenna, which the internal signal processing software flags to trip the alarm. To deactivate these sticker tags at the cash register, the system uses a deactivation pad that emits an intense electromagnetic field at the exact resonant frequency. The induced current traveling through the tag's internal coil generates an induced voltage that intentionally forces a dielectric breakdown by exceeding the breakdown voltage limit of the capacitor's thin insulating layer. This creates a microscopic, permanent short circuit between the capacitor plates, causing the capacitance to collapse to zero. The circuit permanently loses its ability to resonate, allowing it to pass through the exit gate silently. The second variant is the acoustomagnetic, or AM system, which operates at 58 kHz. AM systems utilize a highly unique physical phenomenon known as magnetostriction, where certain ferromagnetic materials change their physical dimensions when exposed to an external magnetic field. This fractional change in length is mathematically defined as lambda equals delta L divided by L0, where delta L is the absolute change in length and L0 is the material's original length. AM tags contain two internal strips, a magnetostrictive amorphous metal strip and a semihard magnetic bias strip. The transmitter gate emits short, alternating magnetic pulses at 58 kHz. The bias strip provides a steady DC magnetic field that tunes the amorphous strip to its perfect elastic operating point, causing it to mechanically expand and contract at high speeds when exposed to the transmitter's pulses. When the transmitter pulse stops during a designated silent period, the amorphous strip continues to vibrate due to mechanical inertia. Through the reverse magnetomechanical effect, known as the Villari effect, this remaining vibration generates a residual magnetic flux that induces a small voltage in the receiver antenna. Because the receiver only listens during these silent gaps, AM systems are incredibly immune to environmental noise, yielding the lowest false alarm rates in the industry. Deactivation is achieved simply by completely demagnetizing the bias strip, shifting the operating point so the tag can no longer physically vibrate at 58 kHz.